Okay, thank you for joining quantum mechanics class with Research Group Discovery. We are going through a book called Quantum Chemistry and Spectroscopy. The second edition by Thomas Engel. This is a pretty readable introduction to quantum mechanics from more of a chemistry perspective. So I'm going to give a lot of descriptions, and at times I will write things on the board. But because we're having this in video format, it is possible to pause it and go back if you miss something. So for the sake of time and trying to keep these on the shorter side, I am going to read important notes and then only write when necessary. So the basic idea about what happens in quantum mechanics is that through a series of experiments, it was discovered that there are things that matter can do that were originally unexpected from the original people that original picture that people had. So the first chapter, which is what we're going to go through right now of this textbook, what it does is it goes through a number of different experiments that were able to be some of the many that demonstrated some of the interesting behavior of matter that had not been previously observed. Now, something that I want to highlight before talking about this is that even though this behavior of the matter might not have been previously really understood or observed as much, because we have gotten better over time at having our sensing capabilities and things like that. But at the same time, that doesn't mean that the behavior of matter is different than it was before. It means matter always acted this way, and this is more a difference in our understanding and our insight and our mathematical description of what matter does. So matter always acted this way, and then you can think of this not as like, oh, matter acts in two ways at once or anything, which will be sort of almost an implication of one of the results of quantum mechanics, which is what people call wave-particle duality, which I'm going to start talking about. I think a good thing to keep in mind is, like, don't get too confused by thinking like, oh, that means a particle is acting like both a wave and a particle and all those things. I think a clear way to think of it, so yes, it has behavior that reminds us of those behaviors that we're used to at a macroscopic level. But I think the real way to think of it is that's the way that matter behaves. So the fact that our mathematical descriptions didn't match up to how it behaved unless we started combining mathematical descriptions of particles and waves is a different story. But the fact is, matter always behaved this way, that it really is more of a mathematical description thing to call it wave-particle duality, rather than to say, like, is it acting like a wave or is it acting like a particle? I mean, it's acting like matter. And I think that's just something important to keep in mind as we're talking about this. So the first thing that chapter 1 talks about is it talks about black body radiation, and it said that there was some cases where classical theory was wrong in some predictions related to black body radiation, and that a major outcome of some of the experiments done was that it sort of appeared that the energy, they say it's the energy of an oscillating dipole or an oscillating electric dipole. I'm honestly not 100% sure what that is, but they said you can maybe think of it as atomic nuclei and their associated electrons, which for me that's also not incredibly illuminating as to like what exactly is an oscillating electric dipole. But just think of it then, I guess, as something sort of at the atomic or subatomic level. It's something sort of like that. But whatever this is, the energy that it has appeared to be discrete. So that was very different than sort of our classical picture of energy, where if you think about what goes on in maybe your first course in physics, you will get things where kinetic energy, for example, depends continuously on velocity. And so as you change the velocity a little bit, you get new energy. This is this is actually an integer. And this here is what's called Planck's constant. And this is the frequency for the oscillating electric dipole. So this was sort of interesting to see some discretization of energy, suggesting that the energy that this oscillating electric dipole has is available in discrete forms, and so that it can't just take any value, and that it doesn't just go continuously, sort of like our standard picture of energy did until that point. So there we go. That's that one. Next one. So the next experiment that this chapter goes through is what's called the photoelectric effect. So I'll put that on the board. Photoelectric effect. So the idea with the photoelectric effect is sort of as follows. So you can have a copper plate in a vacuum. Light incident on the plate can be absorbed, leading to excitation of electrons to unoccupied energy levels. And then sufficient energy can be transferred to the electron such that some of those electrons leave the metal and are ejected into the vacuum, and an electron emitted from copper upon this illumination can be collected by another electrode in the vacuum system called a collector. And so the textbook says that this process is called the photoelectric effect. And so an experiment was designed that kept energy conservation in mind, and the result of this experiment was to, again, relate energy to frequency. So in this case, what happened was that it was postulated that the energy of the electron is equal to some linear function with respect to frequency minus some type of binding energy that the electron has to staying in the copper. And then, so this is the energy of the electron, so electron energy when it gets emitted from the copper surface. And then this is some constant that they were going to determine in this experiment, and then it was hypothesized that here's the frequency of the light hitting the surface. And this is what they call a work function, and they say it can kind of be thought of as almost like an ionization energy. It is the binding energy of the electron in the solid. So the result of this experiment then, the data that they obtained, indicated that this B was again H. So if you think of what we just said a minute ago, where for the black body experiment, they said that the energy of the oscillating electric dipole was equal to H times, or NH nu, where N was some type of integer. Here they again get that there's H nu for the energy of the electron appearing, and here it would be like N is 1. So several weird observations subsequently inspired some of the interesting concepts about wave-particle duality. So this is meant to help with indicating the way that the energy seems to depend on the frequency of light. In the prior experiment with the photoelectric effect, it indicated some type of quantization of the energy. This experiment also indicates some interesting things. So beyond what's written here, some of the stuff that happened when they ran this experiment was that the number of electrons emitted would be proportional to the light intensity, but the kinetic energy would be independent of the light intensity. The number of electrons emitted, unless the frequency was above a threshold frequency, or no electrons were emitted unless the frequency is above a threshold frequency, even when the light intensity was very high. The kinetic energy of the emitted electrons depends on frequency with the linear slope. And the last one that is very interesting is that electrons were emitted even at such low light intensities that the light absorbed by the entire copper plate is barely enough to eject a single electron based on energy conservation considerations. So what this implied was something kind of strange. What you can see about that idea is that it sounds then like that light must be sort of localized. So somehow that light is still ejecting an electron, so if you divided it across the whole plate, you wouldn't have enough in any given location to eject an electron, because barely is the amount absorbed by the entire plate going to be able to eject a single electron. But when they did this, they still found some electrons getting ejected. So this almost suggests that somehow that light is localized, that it's not just constant, that it's not spreading across the entire thing and therefore not ejecting any electron, but that it's sort of finding an electron and going there and ejecting that one and spending its energy right there. So this was one of the things that gave the concept of a photon to describe a spatially localized, or you can think of that as sort of particle light or particle-like light packet. And so that was one of the interesting things about quantum mechanics with respect to wave-particle duality. So usually we think of light as being a wave in a classical sense, but what that experiment suggests is that the behavior of the light is almost, in some aspects, like that of a particle, in that it seems to be finding an electron and then ejecting that one instead of being just uniformly distributed. So this suggested that light has what we call this wave-particle duality, but as I mentioned, an easier way to think about that is to say light behaves as light. We hadn't been capable of observing some of these effects before. When we started to observe them, what was noticed is that in specific circumstances, you're able to observe effects that would not be described by the classical mathematical models that we had, and required us to rethink our mathematical description of matter in order to be able to match our mathematics to the physical situation and to match our understanding to what really happens. So then people said, okay, well, isn't that weird? Light kind of seems to behave sometimes like a particle, so could we go the other way? Could we say that particles behave like waves? And one way of trying to look at that was to say diffraction of electrons by a crystalline solid, which would be more like a wave thing to expect for diffraction. And so then it was suggested by someone named Louis de Broglie back almost 100 years ago that if that we should be able to treat particles as having wavelengths. So then the idea was to say, okay, so here's the wavelength of a particle is equal to h over p. So here is the particle wavelength, and then this is Planck's constant for what I'm going to say. It's going to be important that I write how big this is. So this is 6.626 times 10 to the negative 34 joule second. This here, p, means the particle's momentum, so it's the mass times the velocity. So let's just look at, oh, and this is the velocity. This is the mass of your particle. So part of the problem here is that in terms of being able to do diffraction, to start to see some of the wave nature of like a particle, like an electron, for example, is that this numerator here is very, very small. So for diffraction, it turns out that that you need to have your diffraction with your grading with really atomic dimensions, because if you look at diffraction theory, you need wavelengths at certain, like your wavelength determines the size of the diffraction gratings that you need to some extent. And even if you get a really, because the numerator here is so tiny, 10 to the negative 34, on the order of 10 to the negative 34, even if you go with super light particles, so even if you get one that is like an electron, so an electron's mass is 9.109 times 10 to the negative 31 kilograms. So even if you get this, so that you start trying to say like, oh, okay, say that I have something on the order of 10 to the negative 34 divided by 10 to the negative 31, if I'm moving my particle at only like a very, very slow speed. So then say it's like on the order of 1. Okay, so 10 to the negative 34 divided by 10 to the negative 31, even if you had kind of a slower speed for such a small particle, then what you're still getting then is you're still getting something on the order of 10 to the negative 3 in your numerator. So what this means is that you really do have to sort of use diffractions with grading on with atomic dimensions. And so what people did when they wanted to test this idea about will electrons and other matter behave in a wave-like nature, for those experiments that were done by Davison and Germer, they were using crystalline solids and were trying to look at diffraction of electrons from those. And since then, there's been looked at diffraction of helium and hydrogen atoms, or sorry, molecules from crystalline surfaces. And so the idea that people were able to actually do diffraction with something like an electron is again evidence of some type of wave-particle duality. And it does suggest that maybe there is a wave equation that we need in terms of talking like we were about how what this suggests is that you need a different type of mathematical equation in order to be able, one second. So what this suggests is that you need some type of mathematical equation that we need to update our mathematical equations. So instead of just all the equations of classical physics, what do we need to be able to describe the type of behavior that we're seeing? And so the idea is that maybe then we need to be describing even physical systems using some type of like wave equation. And so that's going to eventually lead to some big developments in the course of this lecture series. But then so in terms of the diffraction experiments that got done, so basically what happened next was that they did some diffraction experiments, and it was very interesting because what they got was that when they used a single electron, there were certain diffraction patterns that they expected. And so they used two different slits. So what that means is that they would have here and here. So there would be two different places that the electron could go through. And they did different experiments where they tried to see, okay, what if I close one of the slits or I close the other or leave both open? And they tried to see what will happen if we try to shoot electrons through these. And where these slits were on that order of size, where they could potentially see diffraction if the electrons did indeed act like particles, or sorry, like waves. So then what they did then is they did get a lot of interesting results. So they saw diffraction patterns indicating a wave-like behavior of electrons, but what they also saw was that when the electrons hit a screen, and that was how they knew it had actually gone somewhere, and when it hit this screen, there would only be evidence of the electron being in one location. But the pattern that got made by sending out many of the electrons was a pattern that you would see in diffraction. So there sort of was a wave and a particle-like nature, and so what the end of this was that these were sort of interesting observations, and they did again suggest this wave-particle duality was going to be important. Since these times, a lot more experiments have been done and a lot of things have been done to try to put together a mathematical framework for describing what seems to be very interesting characteristics of the real world. And so a lot of the way that mathematically we describe quantum mechanics is actually quite interesting. There are going to be things that will come up where the idea would have been that the diffraction patterns couldn't have happened unless there was some way that the particle could have gone through both slits, was sort of how people were thinking of it. So then some of the theory of quantum mechanics involves people saying, well, maybe we can describe mathematically what we're seeing as that there are superpositions of wave functions. So for this case, it would be like the wave function is in a case where it could be in both slits because it's like a sum of it being through either one. And then when you measure it, it collapses to one of those. So then there's all these things about superposition, about measurement, all these things come about, and they're able to describe what was seen in the experiments. And so that's very interesting. They do kind of go in a very interesting way, so whether or not that is really the way that the world works, or if that's just our current mathematical description, I think we'll have to see with time. But yeah, that's the basics of the first chapter of that textbook, and so thanks for coming into lecture.